We usually think of the solar system as a finished product, a static arrangement of planets and moons that has looked the same for billions of years. But interestingly, new data from the mission suggests that Saturn is actually in the middle of a massive, temporary transformation. If you look at the rings of Saturn, they seem like a permanent fixture of the outer solar system. For a long time, the assumption was that they formed alongside the planet roughly 4.5 billion years ago. But during the Cassini Grand Finale in 2017, researchers like Luciano Yes at Sapienza University of Rome used the spacecraft's radio link to measure the gravitational pull of the rings. They found something that broke the old models. The rings have a surprisingly low mass, roughly 1.5 times 10 to the power of 19 kilograms, which is only about 40% of the mass of Saturn's moon Mimas. And this low mass is a problem for the old age theory. If the rings were billions of years old, they should be dark and soot-covered from the constant bombardment of interplanetary dust. But these rings are nearly pure water ice, which means they are bright and relatively clean. So, it turns out the rings are likely a recent addition, perhaps appearing only 10 to 100 million years ago. To put that in perspective, while dinosaurs were walking on Earth, Saturn might not have had rings at all. But I guess the question here is, how did they get there? The data suggests a massive, icy moon may have wandered too close to Saturn's Roche limit, the point where the planet's tidal forces are stronger than the moon's own gravity. The planet essentially shredded the moon into the billions of ice fragments we see today. But interestingly, this beauty is temporary. Data from the Keck Observatory and the Ion and Neutral Mass Spectrometer, INMS, shows that Saturn is eating its rings. This process, known as ring rain, occurs as ultraviolet light charges the ice grains, causing them to spiral down the magnetic field lines into the atmosphere. We are losing about 10,000 kilograms of ring material every second. At this rate, the rings will be gone in less than 100 million years. We just happen to be living in the brief window of time where they exist. For a long time, the standard model of gas giants was fairly straightforward. You had a massive envelope of hydrogen and helium surrounding a small, dense, rocky core about the size of Earth. But interestingly, recent data from Christopher Mankiewicz and Jim Fuller at Caltech has completely upended that internal map. They didn't use a probe to go inside, they used the rings as a giant seismograph. This field of study is called chronoseismology. It turns out that Saturn's internal oscillations create slight fluctuations in its gravity field, which then pull on the rings and create spiral waves. By measuring these waves with Cassini's imaging instruments, researchers found that the core isn't a solid ball of rock at all. Instead, it's what they call a diffuse core. This fuzzy center isn't just a few thousand kilometers wide, it actually extends out to 60% of the planet's total radius. It's a chaotic slurry of ice and rock mixed with liquid metallic hydrogen. So, as you move toward the center of Saturn, there is no hard surface to land on. Instead, the concentration of heavy elements slowly increases until you reach a pressurized, liquid-like soup. But I guess the question here is, why does this matter? If the core is diffuse, it means the heavy elements are distributed throughout a much larger volume than we thought. This changes our entire understanding of how planets form. According to the core accretion model, you need a solid seed to pull in gas. If Saturn's core is a diluted mess, it suggests that the interior is much more dynamic, with materials constantly mixing and moving rather than settling into neat layers. But interestingly, this lack of a solid boundary also affects how heat moves through the planet. Without a distinct core mantle boundary, the thermal evolution of the planet is much slower, which leads to another problem entirely. Why is Saturn so much hotter than it should be? If you look at the thermal balance of the outer planets, most of them follow a predictable cooling curve based on their age. But interestingly, Saturn is a massive outlier. It radiates about 2.5 times more heat into space than it receives from the Sun. While some of this is left over from the planet's formation, that doesn't account for the total energy output. Standard cooling models suggest Saturn should be much dimmer and colder by now. This discrepancy led researchers to a process that sounds like science fiction but is a mechanical reality in the deep interior: helium rain. At specific pressures and temperatures deep within the hydrogen envelope, roughly 2 million atmospheres, helium becomes insoluble in hydrogen. It's similar to how oil separates from water. Because helium is denser, it condenses into droplets and falls toward the center of the planet. As these droplets sink through the lighter liquid metallic hydrogen, they release gravitational potential energy in the form of heat. This process, theorized by researchers like David Stevenson at Caltech, effectively creates an internal heater that has been running for billions of years. But I guess the question here is, what does this do to the planet's structure? It turns out this rain creates a compositional gradient. The outer layers of Saturn are actually depleted of helium compared to the Sun, while the deeper layers are enriched. This isn't just a chemical shift, it affects the entire fluid dynamics of the planet. The falling helium creates massive convective currents that drive the violent weather patterns we see at the surface, including the Great White Spots, gigantic storms that wrap around the entire planet every 30 years or so. But interestingly, this internal rain might also be responsible for another Saturnian anomaly: its bizarrely perfect magnetic field. By redistributing mass and heat, the helium rain may be stabilizing the flow of metallic hydrogen, but in a way that contradicts almost everything we know about planetary dynamos. If you compare Saturn to Earth or Jupiter, the magnetic field presents a massive theoretical problem. On Earth, the magnetic North Pole is tilted about 11 degrees away from the rotational axis. On Jupiter, it's about 10 degrees. This tilt is actually a requirement for most versions of dynamo theory, which explains how the motion of conducting fluids, like liquid metallic hydrogen, generates a planetary magnetic field. But interestingly, data from the Cassini magnetometer, MAG, led by Michelle Dougherty at Imperial College London, showed that Saturn's magnetic axis is aligned with its rotation to within less than 0.01 degrees. By all standard rules of physics, this shouldn't be stable. A perfectly symmetric dynamo should eventually decay and disappear because there's no wobble to drive the complex fluid motions needed to sustain the field. But I guess the question here is, how is the field still there? It turns out the answer might lie in the layers above the dynamo. Researchers suggest that a stable, non-convecting layer of helium-rich fluid, the result of the helium rain we discussed, might be acting as a spatial filter. Essentially, this layer sits on top of the churning metallic hydrogen and screens out the non-axis symmetric parts of the magnetic field. So, the field being generated deep down might actually be tilted and messy, but by the time it reaches the surface, we only see the perfectly aligned components. But interestingly, this perfect alignment makes it nearly impossible for us to determine the exact length of a Saturnian day. On other planets, we track the rotation of the magnetic field to find the true day, but because Saturn's field is a perfect circle, there is no pulse to time. We've had to rely on complex wave patterns in the rings just to guess that a day is roughly 10 hours and 33 minutes. When we look at Saturn, we are essentially looking at a snapshot of a catastrophe in progress. We usually assume that planetary features are permanent, but interestingly, the data from Cassini's Cosmic Dust Analyzer, CDA, suggests that the rings are a fleeting spectacle. If we had evolved a few 100 million years earlier, or a few 100 million years later, the night sky would look fundamentally different. The rings are currently being drained by ring rain and gravitational torques from moons like Enceladus, which is itself a violent engine of change. As Enceladus orbits, it sprays water vapor and ice grains into space via cryovolcanism at speeds of 400 meters per second. This material doesn't just form the faint E-ring, it also rains down into Saturn's upper atmosphere, altering its chemical composition and cooling the ionosphere. So it turns out that Saturn is an interconnected system, where the moons, the rings, and the planet's deep interior are all actively exchanging mass and energy. But interestingly, this means the Saturn we see today, with its bright, expansive rings and its fuzzy core, is a transient state. But I guess the main idea here is that Saturn isn't a finished monument. It's a dynamic, cooling giant that is rapidly losing its most iconic feature: The mismatch between our old static models and this new high-density data shows that the outer solar system is far more volatile than we imagined. Future missions like the proposed Enceladus Orbilander or deep atmospheric probes will likely focus on how this internal helium rain and the ring loss process are physically linked. So it turns out that the most terrifying thing about Saturn isn't just its size or its storms, but the fact that it is fundamentally unstable. We are simply lucky enough to be watching during its most beautiful century.